In November 2011, experts from around the world gathered in the town of Araxá in Brazil to attend a seminar entitled Welding of High-Strength Pipeline Steels. This international seminar was hosted by CBMM, Companhia Brasileira de Metalurgia e Mineração, the world's largest producer of niobium, and TMS, the Minerals, Metals and Materials Society. Dr. Tadeu Carneiro, Chief Executive Officer of CBMM, explains the concept behind the seminar.
This format of symposium or conference that CBMM put together is a very important tool in our market development program. They are designed to bring all the important researchers and professionals from universities, from customers, steel makers, end users, the whole supply chain, bring them all together to solve one specific problem. So in this case, the main theme was weldability and welding of niobium steels. We were very successful and we are very pleased that we were able to bring more than 120 delegates this time, all by invitation, and representing representing 17 countries, as a matter of fact. And so it's truly international and very focused. So in these 3 days that they were together, they could exchange ideas, they could discuss those myths, they could set the record straight, and we get a very fresh inventory of ideas to move on with our market development program in solving problems that our customers have and pushing to an additional level, to a higher level, our niobium technology for the steel industry and the final solution. So we are very pleased with the results, and we're actually looking forward to running the action list that came out of this symposium now.
The delegates received a warm Brazilian welcome to Araxá. Children from the local school greeted the international visitors with traditional Brazilian songs. And then the guests were invited by CBMM to plant a tree to commemorate their visit. This is customary for all CBMM's visitors, and everyone was encouraged to return to Araxá to visit their tree. A tour of CBMM's facilities followed, where delegates saw the mine, the world's largest deposit of niobium ore. This was followed by a tour of the mill, processing plant, and research and technology center. They saw the whole process from extracting the ore to the final products: ferroniobium, niobium oxide, and pure niobium. CBMM's Conservation Center and Chinese Garden were also a feature of the tour. The seminar program included a formal dinner with entertainment from Groove Allegro, a fusion of samba, choir and orchestral music. And ended with a trip to Rio de Janeiro, where the delegates could relax and enjoy the sights including Sugarloaf Mountain and the Corcovado. The seminar was officially opened by Tadeu Carneiro, who welcomed the delegates to Araxá. In total, during the 3-day seminar, 26 papers by 77 authors were presented on topics ranging from microstructures to projects involving thousands of kilometers of pipelines. During the official opening of the conference, Tadeu Carneiro made a special presentation to Dr. John Malcolm Gray from the Microalloyed Steel Institute in the USA for his long-standing support of CBMM and his promotion of niobium technology during the past 50 years. Dr. Gray then set the scene for the seminar by presenting a paper detailing the history of the use of niobium in line pipe steels. The story begins back in 1959, when a small addition of niobium, less than 0.01%, was first added to a carbon manganese steel to allow the production of the X52 grade. At that time, a carbon level of 0.25% was fairly typical. But in the intervening years, advances in oxygen steelmaking, plate rolling mills, and our metallurgical understanding mean that it is now possible to produce X80 grade material at carbon levels below 0.05%. Such low carbon levels, combined with advanced higher temperature rolling schedules, allow the effective utilization of much higher levels of niobium, typically around 0.1%. Such steels are commonly referred to as HTP. Dr. Gray observed that millions of kilometers of niobium-containing line pipe steel have now been successfully installed worldwide. And with reference to the more recent advent of the X80 grade, he highlighted the dramatic progress made in China in the last 8 years, where major projects such as the second West-East cross-country pipeline are consuming vast tonnages of HTP high niobium X80. The latter remarkably ambitious project, completed in June 2011, which now transmits gas at operating pressures up to 12 megapascals, incorporates some 4,895 kilometers of 48-inch diameter pipe with wall thicknesses up to 27.5 millimeters. In all, some 4 million tons of material were involved. He noted that dramatic improvements in weldability had accompanied the material developments that he had described, indicating that these would be more fully explored by subsequent speakers. International consultant Dr. Phil Kirkwood from the UK then presented the seminar's keynote address with a paper entitled Niobium and Heat-Affected Zone Mythology. Emphasizing the unique nature and special characteristics of the element niobium, and with reference to comprehensive studies by world experts over the past 4 decades, Dr. Kirkwood successfully dispelled the myth that niobium levels in structural and line pipe steels should be arbitrarily restricted, because some researchers had apparently concluded that the element could be responsible for the occurrence of low toughness in small regions of certain welded joints. Dr. Kirkwood effectively demonstrated that, taken out of context, individual sets of results could readily be used to demonstrate that any of the common primary alloying elements, such as manganese or nickel, could just as easily be shown to be detrimental to heat-affected zone toughness. More importantly, he reiterated his previously published belief that the optimum use of niobium will always occur when its incorporation into a steel composition is an integral part of a carefully tailored approach to specification, taking due account of the welding processes which will be encountered in the practical fabrication and joining of lengths of pipe. In this context, Dr. Kirkwood demonstrated the powerful interacting effects of carbon, niobium, and the thermal cycles associated with common welding processes. The lower carbon levels, now associated with the most recent pipe developments, enable higher niobium levels to be utilized over a much wider range of heat inputs to produce pipes with more than adequate heat-affected zone toughness, meeting the demands of even the most rigorous fabrication specifications. Dr. Kirkwood presented explanations for his conclusions based on a widely accepted coarse-grained heat-affected zone toughness model, which had been developed several years ago. His address continued to challenge aspects of the specification of toughness requirements for small microscopic regions of welded joints, and this was subsequently more fully explored by other presenters later in the seminar. Concluding his remarks, Dr. Kirkwood reminded delegates that the progress made by the adoption of the new HTP technology required progressive thinking and engineering, such as that demonstrated by the Chinese, and he warned of the danger of being deterred by the mythologies of earlier literature. Over the remainder of the seminar, in 4 carefully arranged technical sessions, specially invited world experts on all aspects of the specification, manufacture, field welding, and fracture behavior of high-strength line pipe steels addressed the seminar. At the end of each session, a panel discussion provided a structured opportunity for delegates to question individual authors, and this approach proved to be highly successful in generating open and frank dialogue. Undoubtedly, one of the key outcomes of the seminar was the demonstration that a remarkable degree of consensus already exists in respect of many of the most important facets of the science and engineering required to optimize the use of the new generation of higher strength niobium-containing line pipe steels. Dr. Kirkwood had shown how adequate heat-affected zone toughness could be achieved, and further interesting contributions by Professors Shang of Beijing University, Badisha of Cambridge University, and Cochrane of Leeds University significantly added to the science of the subject by improving our understanding of why certain types of microstructures were tough while others were not. Several authors at the seminar, including Professor Shang, presented microstructural analysis using the relatively novel electron backscatter diffraction (EBSD) technique. Professor Badisha presented an interesting account of the way in which martensite-austenite Ma constituent develops in heat-affected zone microstructures, and demonstrated how chemical composition and basic transformation theory could be used to predict its nature and volume fraction. As discussed in Dr. Kirkwood's keynote lecture, Professor Badisha observed that Ma was an inevitable consequence of the displacive bainitic transformation, and his explanation supported the view that carbon, and probably silicon, could increase the volume fraction of Ma. Although claims have been made in the literature suggesting that niobium may promote increased levels of Ma, this contention is not supported by either Professor Badisha or Dr. Kirkwood's studies. Dr. Kirkwood concludes that if this is an area of concern, the simplest solution is to reduce carbon and silicon as in the HTP steels. This approach reduces Ma to the lowest possible levels. Amongst other papers concerned with the role of microalloying elements on heat-affected zone toughness, an interesting contribution came from Lee Fletcher and co-authors from Australia. The paper, presented by Hoijun Lee from the University of Wollongong, explored the effect of titanium to nitrogen ratios in niobium-bearing line pipe steels. He concluded that so long as titanium remained below 0.06%, there was no justification for specifications to demand titanium to nitrogen ratios below the stoichiometric value of 3.42. Further important contributions were made by Frantov, Militsa, Manohar and Guanyeli, and the co-authors of all these contributors. The outstanding Chinese successes with high niobium HTP type X80 steels, which were referred to earlier by Drs. Gray and Kirkwood, were described in detail by Professor Shang and also Madame Zhao of the China Petroleum Pipeline Research Institute. Professor Shang attributed the Chinese success not just to the availability of new, more effective steel processing equipment, but to their willingness to accept the challenges of the new emerging materials technology. And Madame Zhao emphasized the importance of the development and optimization of field girth welding procedures. Professor Shang confirmed that it was the Chinese's ready acceptance of the pioneering work in North America and their confidence in the contemporary metallurgical development work which convinced them to set aside the arbitrary restriction of niobium to a maximum level of 0.06%. The latter figure is still currently embedded in the relevant API and ISO specifications. For the major X80 projects already alluded to, they produce their own specification to allow up to 0.11% niobium. This approach was supported by other key speakers, such as Dr. Krishnan, an eminent consultant from India, who had been instrumental in enabling similar progress in respect of niobium levels in Engineering India Limited specifications for X80 pipe material for the Gas Authority of India. Dr. Noop, in discussing the manufacture and supply of large-diameter helically welded X80 pipe in Germany, also emphasized the advantages of the HTP approach, indicating that the relevant Euro norm for steel pipes for combustible fluids, which also limits niobium to 0.06%, is no longer sustainable and must be revised. Reporting on the outcome of a 3-year European project which assessed the potential of steels with higher niobium levels, consultant Dr. Webster also advocated the rationalization of world specifications and supported Dr. Noop's contention that the appropriate pipe steel's Euro norm was in need of urgent revision to embrace the new HTP technology, He suggested that with low-carbon steels, evidence from the European project supported his own belief that specifications could safely permit niobium levels of up to 0.15%, and supported Dr. Kirkwood's conclusion that the new higher niobium approach was ripe for technology transfer into the fields of structural, shipbuilding and pressure vessel steels. Dr. Webster felt that the first step should be the revision of the Euro norm for thermomechanically rolled structural steels to permit niobium levels well above the current limit of 0.06%, and in principle he could identify no technical barrier to niobium levels up to 0.15% in low-carbon steels. In papers by consultants Drs. Glover and Krishnan, the relative costs of pipe material and construction were explored. Depending on the specific project, material costs can account for between 25 and 40% of overall project costs. But in Dr. Krishnan's experience, pipe construction costs are dominant and can easily be up to $1.5 million per mile of completed pipe. These factors together support the drive towards higher strength pipe, such as X80, and reduced wall thicknesses to reduce the volume of weld metal required in the field and permit installation in the fastest possible time using high-productivity multi-arc GMAW processes. Drs. Glover and Krishnan and Professor Shung alluded to the possible use of X100, which had already been pioneered in a small pilot project in relatively hostile conditions in Alberta, Canada. It was agreed that any potential global move in this direction would be driven by the economies of scale if the particular project allowed full advantage to be taken of a higher operating pressure. The material and welding technology already exist, and Dr. Krishnan confirmed that there is at least one major project under serious consideration by a consortium in India. Higher pipe strengths have the potential advantages of lower tonnages, lower material costs, reduced handling costs, improved field logistics, and reduced welding costs. However, Dr. Glover observed that account had to be taken of the significant reduction in usable ductility, which he estimated to be between 4 and 5% at X100 and between 1 and 2% at X120, which would almost certainly require a pipeline design relying on crack arresters. At present, X80 appears to be the optimum approach for most major projects. Dr. Gordon from Microalloying International emphasized that the majority of existing onshore pipeline design codes are stress-based and don't properly account for situations where high strain is experienced during installation or operation. Similar observations were made by Dr. Glover, who reminded delegates that traditional design used the allowable stress design approach based on some factor of yield stress. Strain-based design becomes essential in challenging areas where the pipe might experience axial displacement and severe longitudinal loading in areas of ground instability or seismic activity. Detailed analytical papers were presented by Dr. Gordon and Professor Dennis of Ghent University, comparing various strain capacity prediction models published by ExxonMobil, the Center for Reliable Energy Systems, and Professor Dennis's own university. There appear to be varying degrees of conservatism, but the models all give weight to the same key variables and permit acceptable engineering critical assessments to be carried out for specific projects. The roles of small and full-scale testing were thoroughly discussed by the various contributors, and curved wide plate tests were demonstrated to be an acceptable means of estimating the strain capacity of floored girth welds. The ability of the various models to allow for the beneficial effects of weld metal strength over matching was highlighted. Dr. Pushmitsev of the Russian Research Institute of the Tube and Pipe Industry also presented some valuable results from full-scale hydraulic tests on large-diameter microalloyed steel pipes, which suggest that the fracture behavior of defects in locally embrittled zones is dictated by the base metal pipe properties. Fracture arrest behavior in spirally welded pipe is improved by the optimization of weld design. Thanking the authors and delegates on behalf of CBMM at the close of the seminar, Dr. Carboni astutely summarized the proceedings, highlighting the major areas of agreement and identifying challenges for the future. There is no doubt that this seminar has been an outstanding success, cementing the progress made in recent years in respect of the application of niobium in high-strength line pipe applications, and providing a springboard for future developments and the translation of the low-carbon, high-niobium technology into structural steel and other important specifications on a worldwide basis. CBMM looks forward to hosting other such events in the future. Now let's hear from some of the seminar delegates and speakers.
Been really enjoying it. It's been a good mix of different papers, different subjects, obviously very educational, but I suppose the real test of a good conference, which this one's been, has been the extensive discussion that's occurred during the assigned sessions and obviously outside of those. And you always get more benefit from that than maybe from the actual papers themselves.
I think that the thing that's really interesting is the work on microstructural effects in the heat affected zone, because you know, for many years we've not had an adequate understanding of what happens to the heat affected zone and what the consequences are of what happens to the heat affected zone in terms of service. So there's been some really good papers on that subject, and that's been really helpful. I think the future is extremely sound. I mean, we've seen the excellent work on the development of the HTP steels with kind of double the level of niobium, and I don't know whether that's the limit. I guess we'll see that over the next few years, but there's lots of opportunities for niobium, and there's been such good developments in pipeline steels with niobium that I'm sure this is going to be transferred into other areas to the benefit of the niobium production industry.
Many experts are gathering here, and of course it's very interesting to look at their presentation, to understand what is important for field they study, and also it's very important for me to share our result, to consider it together with excellent team of experts here during conference days here.
I think it's very clear that the material scientists or metallurgists have learned a great deal from the engineers who actually install the line pipes in the field, and vice versa. And I think the more dialogue we have of this kind, the more the better the direction in which we do our research. For new friends.
For this conference, this seminar is perfect. And the topic of the technology is very important, especially for the welding. Welding is very complex technology, more complex than the steel products themselves. So this conference is very good. A lot of the experts make the presentation, introduce what they did, how to solve some production problem, and also let the people, the expert, to know each other.
Undoubtedly, this will turn out to be an event of major importance, and I particularly enjoyed listening to Professors Cochrane and Bayadisha, whose work appeared to slot in well with my own keynote presentation. It's been great to come back to Arasha after so many years. It's an ideal venue for an event of this nature, and it's great that CBMM have been able to pull together so many world experts. When this event is over, several of us will sit down and discuss what we think we've learned, and we will undoubtedly develop some new ideas for further research, probably at different universities and research facilities throughout the world.